So to the main event, I'm really delighted that we have Sergey Kiselev, who is head of Europe for ZeroAvia, and we're going to learn about the practicality of hydrogen as a fuel for flight. I should mention for questions, I can say this again at the end, people in the room wait until a microphone reaches them, and people online use the Q&A box for your questions, but I'll repeat that again after the lecture. But Sergey, thank you very much for coming to Cambridge. We look forward to your talk.
Thank you very much. Can you hear me? Excellent. So I'm going to talk about a few different things. One of them is, of course, hydrogen, because this is one of the, I guess, main topics or main fuels which we understand is hopefully going to solve the problems with making aviation sustainable. But also I will talk about the history of the company. And I guess the name of the application research is, I guess, forcing me to talk about how do we think about research? How do we think about the development? And then how do we make it, how do we put it in practice and realize in what we do, okay? So it will be a bit of the hydrogen introduction, and it will be a bit of the history and the journey of ZeroAvia and why we are doing this and where we're going. The clicker doesn't work. Okay, so first hydrogen. So right before the talk, we were talking about different types of hydrogen, and this is where I tried to put a little description of the hydrogen ecosystem. So hydrogen is actually one of the molecules which is produced at scale in the industry. And mostly it is produced, it is 80 to 100 million ton of hydrogen produced globally. Mostly it's produced at the big oil refineries and used for cleaning up the oil and producing our gasoline, which we are using quite extensively now in transportation. But also it's used for producing fertilizers. So this is primary uses of hydrogen nowadays. Now, just if you look at how hydrogen is produced, so we call it has different colors. So the most common source of hydrogen is the natural gas, and if you produce hydrogen from natural gas, it's called gray hydrogen. Now, if you capture CO2, which is produced during production of hydrogen from natural gas, it will be called blue hydrogen. Okay. Now, then of course there is brown hydrogen if it's produced from coal. Then there is pink hydrogen if it's produced from the electricity which is produced by nuclear power stations. But for us, for ZeroAvia and for the industry to actually bring a clean hydrogen into all different uses, we would like to use hydrogen which is produced by low carbon or no carbon sources. So those are, for example, the solar and wind and the hydropower stations, which are producing electricity, and then we are using electrolysis to just split water into hydrogen and oxygen. And then in that case, it will be primarily green hydrogen. And that green hydrogen, which is produced without any production of CO2, will be used by us later in all our activities and in all the other uses. So the other uses which are anticipated now is, and the hydrogen economy is actually growing quite significantly, or at least there is a huge desire to boost the hydrogen economy, and there are a lot of uses which can use hydrogen at scale. So, for example, hydrogen can be used for heating at homes. Hydrogen can be used in all the different types of transportation. Now, for example, in the streets of some of the cities in the United Kingdom, we have hydrogen buses. So we have hydrogen Toyota Mirais, which are driving and also on the roads. And of course, we are producing engine for powering aircraft. Okay, so now that green hydrogen can be used, of course, not only in transportation and in heating of our houses, but also in a very hard to abate or CO2 abate processes. For example, in steel production, for example, in cement production or the fertilizer production. And that hydrogen, which I talked about at the beginning, the green hydrogen, will be used in those industries as well. So why are we talking about hydrogen now? Because, as I said, hydrogen can be used in a variety of different applications, which are very hard to abate. But also, the price evolution of hydrogen is incredible. So you can imagine what happened to the development or the cost evolution of renewables. So about 20 years ago, it was prohibitively expensive to use solar and wind power generation, and now they are very competitive with the traditional power generation. Why? Because there was a lot of government support, of course, and the scale actually generated the decrease in the cost of technology. The same thing is going to happen with hydrogen. So the cost of the electrolyzers is decreasing. The cost of the renewable power generation, which is used to produce hydrogen in these electrolyzers, is decreasing as well. So net, you will see that in the next 10 years, the price of hydrogen will decrease actually from today's, let's say $6 to $10 per kilogram to about $1. Okay, so we are expecting drastic decrease in cost of hydrogen in the next years. And actually, a lot of sources, a lot of very respectable sources of information, research, and analytics. So, for example, Bloomberg New Energy Finance and International Energy Association, they are predicting that there will be quite significant uptake of hydrogen. So, for example, 30% of all the emissions will be avoided just by use of hydrogen, and about quarter of energy will be produced by using hydrogen. So now, why are we thinking about hydrogen in aviation? Because today, aviation is contributing about 2 to 3% of global CO2 emissions. But this is direct emissions. So if you calculate the environmental impact from burning traditional fuel and using it for propulsion in aviation, then the environmental impact will be actually 5 6%. Some researchers say that it can be actually as high as 10%, because there is not only direct CO2 production, but there is also the nitrogen oxide, there is soot produced, and there are contrails which you can see in the skies when the airplane passes by. So and a lot of other industries are doing quite a bit to actually abate or decrease environmental impact. And if aviation doesn't do anything, we are very easily go from about 5 to 10% of environmental impact to about quarter to 50% of the environmental impact. And our travel, even now, it's not guilt-free, but by 2050, it will be absolutely not guilt-free. And this is exactly why there is quite a bit of research and development going on right now into how to actually decarbonize aviation. And there are a lot of different techniques or sources of fuel which are considered. And I guess the main ways to decarbonize, on top of course, the improvement of efficiency of the traditional engine, of improvement of the dynamics of the wing, et cetera, which can reduce the emissions by about a quarter or 25%. So then the rest will be still emissions from burning the fuel. So what are the alternatives? The alternatives are, for example, the battery electric. So we drive Teslas, we drive electrical vehicles, and you can see that it's there are at least no tailpipe emissions which we generate by using electrical vehicles. But unfortunately, battery electric is not scalable. So in order to, I think one of the executives in one of the airlines said that in order to actually fly a 320, Airbus 320, some considerable distance, you need to have, I think, 80% of the aircraft filled with batteries. Okay, so and that will allow you to actually take off and land pretty much. Okay, so the battery electric, even if it produces no direct CO2 and no induced CO2, so it's not scalable because it's very heavy. Okay, so it can do small distances. So for example, 50 kilometers or 100 kilometers, but nothing on the longer scale. Now there is a lot of discussion about sustainable aviation fuels. So those fuels are produced from different feedstocks. So for example, from fats, which are produced in cooking, or similar type of waste sources of energy. And you can actually refine that, and you can produce fuel which is similar to aviation fuel. And the reason why it's called sustainable aviation fuel, because there is a very small direct CO2 emission, because that fat or those products or byproducts would still emit CO2. Okay, but when you burn sustainable aviation fuel, you still produce all the byproducts, which, as I said before, they can contribute to as much as direct CO2. So that is, while it will decrease quite a lot of emissions, roughly by half, but they will not eliminate all the emissions. Now we get to the topic of application of hydrogen to aviation. So there are two main technologies which can be used. One is, of course, you use a traditional turbine, which are used on the aircraft. And instead of using the jet fuel, you can use hydrogen and you can combust it. Of course, you would need to change the turbine a bit or quite a bit, but there will be the byproduct will be mostly water. But because there is a lot of the temperature inside of the turbine is so high that water, which is produced by recombination of hydrogen and oxygen from the atmosphere, it brings in a lot of nitrogen from the atmosphere. And nitrogen and oxygen at very high temperatures, it produces nitrogen oxides as well. So in order to avoid that, we are using quite a different technique, not hydrogen combustion, but hydrogen fuel cells. Hydrogen fuel cells, the highest, they're using electrical chemical reaction, and the basic electrochemistry of the process is such that you have a membrane which is transmits protons to the other side of the membrane, and the electrons which are produced by splitting hydrogen molecule into protons and electrons. Electrons produce electrical current, and on the other side of this membrane, you have recombination of protons, electrons, and oxygen molecules on the other side. So the highest temperatures which we reach inside of the hydrogen fuel cells is about 100 degrees Celsius. And that's not enough to produce any of the harmful nitrogen oxides or any other byproducts except for water. And if you come to our airport in Cotswolds, we are based in Campbell, which is very close to Cirencester, and you observe the testing of our aircraft. You can see a lot of steam which is coming out of the aircraft, and this is the only byproduct which we are anticipating. Okay. So the beauty of hydrogen is that, which is used in hydrogen fuel cells, is that it is scalable. It is actually 100 times more energy dense than battery electric. If you do the calculations, you will see that we can actually achieve the duration of the flight about 5 to 10 times higher than for the battery electric, and we can, as you will see during today's presentation, that we can see the technological roadmap which will allow us to fly larger and larger aircraft. What we are anticipating will happen at the airports will be, of course, our aircraft. So it is fueled by our refueler, which we implemented again at our airport. It is serving as the hydrogen storage and hydrogen dispensing unit, and we will have hydrogen production using electrolyzer on the airport. And of course, that is the electricity which is used to produce hydrogen will hopefully be also produced, in the vicinity of the airport. So you can actually anticipate the situations where the airports will be pretty much independent in terms of the energy. Okay, so it will be locally produced electricity, locally produced hydrogen, and then we will use that hydrogen for the aircraft. So what does ZeroAvia do? And I think that this is what we are doing is basically solving technological blocks which will enable what I just talked about. So the heart of the engine, or the process of transferring the energy from hydrogen into propulsion, is the engine of the aircraft. Our engine consists, this is the basic schematics, and I will go through the building blocks of that. So the propeller, it is not what we are doing. But the propeller is connected to the shaft. On the shaft, we have electrical motor, similar to, again, the electrical vehicle. So electrical motor is powered by electricity, which is produced inside of hydrogen fuel cell. And that hydrogen is stored on the aircraft in some sort of storage. Okay, so we are implementing actually everything past this line. So we don't do the propeller, but everything else we implement on the aircraft. Going forward, we anticipate that the hydrogen storage will be actually also realized by the aircraft manufacturers, and we will produce only the engine itself. Okay. So our roadmap includes, of course, flying small aircraft and then going to larger aircraft, and going all the way to intercontinental, long distance flight using hydrogen. So we have flown already the 6-seat aircraft in 2020, and at that time we were located at Cranfield on Cranfield Airport and at Cranfield University. Now we are actually we just finished ground testing of our 19-seat aircraft, and hopefully in the next couple of days we have a date in mind, but weather in November in that part of country, so it can be quite unpredictable. But hopefully we are going to fly in the next few days 19-seat aircraft, and that will be the largest. When we flown the 6-seat aircraft, it was the largest commercial size aircraft flown in the world. Now using the hydrogen fuel cell technology. So now, of course, when we are testing the 19-seat aircraft, it will be, we will set up, we will break another record, and we are going to then work on the larger and larger aircraft. So how did it all start? And this is a picture. So the company, by the way, is about 5 years old. So on the 3rd of November, we had the 5th anniversary of the company. And this picture is about 4 years old when we implemented our first test rig. And this is the flying El Camino, as we called it. It was done in Hollister, in California. So basically, we used this is the test rig or the copper bird, which utilized the propeller, the electrical motor assembly, all the cooling, and hydrogen fuel cell, which is located in the trunk. So our company is a strong believer in incremental approach. So we don't announce our plans to build the 100-seat aircraft in the next decade or two. So we believe that we need to go from the small to larger, to larger, to larger. And the next incarnation or test bed of our technology was on the 6-seat aircraft, and we basically cut off the traditional engine and installed our electrical engine inside, and we have flown it about 4 years ago, again in Hollister, in California. And then we received a grant from Innovate UK, and the only condition for that grant was that we will move our hydrogen research here to the UK. And this is when I started to work at ZeroAvia about 3 years ago. We had only 3 people back then, and we replaced the battery electric engine, which was on the previous slide, and we put a hydrogen fuel cell on the front of the engine. At that point, the hydrogen tanks were inside of the aircraft, and I guess the idea for the you saw in one of the pictures that the idea for the commercial aviation is that when we implement it on the 19-seat aircraft, the hydrogen tanks will be mounted outside. And it was flown in September 2020. We had pretty impressive coverage in all the Sky News, BBC, etc., etc. And it was a very important point for the aviation in general, because when I joined ZeroAvia about 3 years ago, as I said, pretty much nobody talked about hydrogen in aviation. So if you go to the conferences, there would be discussions about the battery electric, it would be about the sustainable aviation fuel, but nobody believed that hydrogen can actually play a significant role in aviation. And it's amazing how things changed, and hydrogen is actually considered to be the only scalable solution in the next few decades. Okay, so this is just a small, a few pictures how we produce our hydrogen. So we have at our first airport in Cranfield, we had there were some solar arrays. We had our hydrogen fuel cells located in a small container. Then we transferred hydrogen into our hydrogen truck, which, as I said, serves not only as a storage, but also the dispenser of hydrogen, which we used not only for the aircraft, but also for our company vehicle, which is Toyota Mirai, which is also using hydrogen. And this is how small the team was. So, when we have flown the aircraft 2 years ago, we had about 10 people who actually worked on this. Now we have about 130, 140 people here in the UK, and about 50 to 60 people in the States, where we are originally from. So now we can call ourselves as UK and US company, not the US and UK company. So when you're a pioneer in the field, it's actually hard to depend on others, and this is what we realized in the implementation of our powertrain. And it turns out that it's even harder to do it in aviation, because every single component which you put on the aircraft, it needs to be aviation certified. It needs to be traced. Every single nut and bolt which you put on the aircraft, and in particular on the engine, it needs to be traced to the origin. Therefore, we are a strong believer that in order to enable our innovation, we have to have a significant vertical integration. And this is exactly what we are achieving by making our own electrical motors. So we are actually testing now, I would say, best in class, the highest power density electrical motor in our lab. It is in stackable configuration, so now it has about 750 kilowatt power. Okay, and it is stackable in such a way that we can power the largest turboprop, which is the largest commercial or passenger turboprop, which is -8 Q400, which requires about 3.5 megawatt per each side. So we can realize that. So we are doing our own power electronics, which is, as you can see, you can integrate our inverters, or the components which convert DC current into AC current, which is necessary to drive electrical motor. We can integrate them together in order to save space and save weight, okay, for the interconnects. We are also using novel ways of putting the hydrogen fuel cell stacks together. But not only that, we just merged with a smaller company, which is producing different type of hydrogen fuel cells, which will be important to actually implement for the larger aircraft. So most of the technology which is used now in transportation is using low temperature PEM, low temperature proton exchange membrane fuel cells. And the new technology is high temperature PEM. And basically, by going from one technology to another, we will be able to save about a factor of 2 in terms of the weight. Okay. So putting all these components together, we will be able to achieve more than 2x reduction in terms of volume and the weight of our powertrain, which is absolutely important for this thing to fly in the sky. Okay, and so this is our new home, and it's you can. You don't hear the noise, the voices, but you can see, you can read it. But basically, this is our final tests of the powertrain, and you can see that we were able to fit, all the electrical powertrain inside of the aircraft nacelle. Of course, many of the components are inside of the aircraft itself, but these were, some of the tests which we conducted in the last couple of months. So basically, all the ground testing and both stationary and the high-speed taxiing were already completed at our location. And as I said, in the next few days, hopefully, we are going to fly. And in order to make this happen, we had to build the team quite significantly. As I said, from 3 people 3 years ago to about 130, 140. And we actually are very happy that we're here in the UK because of the concentration of the local talent, not only, of course, supportive government, which helped us to move our research and development here, but also the local talent, which is quite amazing. And of course, we would like to have more people working with us. But yeah, so and the more we fly, the more people will believe in hydrogen in aviation. So this is our 19-seat aircraft, and in parallel, we are working on developing the larger powertrain, which will actually be able to power the aircraft similar to what is flying, for example, Flybe or Logan Air. This is or Arini, which flies to Channel, to Guernsey, Channel Islands. So this is already the larger 40 to 80 seat aircraft. We already started the development, as I mentioned already, the motors, the electrical motors, and hydrogen fuel cell systems, which we are testing in the labs. They will enable us to actually do the tests on the ground, and we already have a bigger. It's not the flying El Camino anymore. It's the military, former military truck on which we are placing our Copperbird, and where we can actually test much more powerful systems. And I will not bore you with a lot of other details, but very often when we talk to the operators, to the airlines, they asking a question about where do you get hydrogen, and do you consider hydrogen or existence or the availability of hydrogen as a barrier or bottleneck in terms of bringing your dream into reality. And actually, it's becoming we don't think it is a problem. And I already outlined how we implemented this solution, but there will be more and more hydrogen produced, both locally and globally. So, for example, you probably know that hydrogen can be transported similar to how natural gas is transported. So, for example, there is a huge export of hydrogen from Australia to Japan. Okay, and there will be similar type of setups available to transport hydrogen long distances. But we are also working on decreasing the price of production of hydrogen. And the way we do it is, I have a PhD in physics, right? So our founder also has a PhD in physics, and we are fans of making our planet more sustainable and cleaner. And one of the ways to do it is, think about how does the electricity is produced, when it is produced, how clean the electricity is used to produce hydrogen. And this is what we implemented, for example, just some simple algorithms. This is example of California. You look at the electricity prices, okay, and you look at how clean the electricity is, and you can do it. There are some information sources which you can pull in order to make that assessment. And you can see that the electricity prices are the lowest, of course, during the night when there is, too much wind, or there is too little demand, when there is a lot of supply. And we turn the electrolyzer during the time when the electricity prices are the lowest. And it turns out that very often it is, during the times when it is the cleanest. And we don't use it when the electricity prices are the highest. And only by doing that, by timing it, we can actually decrease the cost of production of hydrogen by, something like 20% or a quarter. So, this is on the side of what we are doing, but we are also thinking not only about how to propel the research and development into the propulsion technology, but also how to make the adoption of this technology much better, cheaper, and easier for the operators. And this is what we see. We see that actually the cost of operation per flying hours. We did this study together with one of the airlines. It can be up to 40% smaller if you switch to hydrogen. Of course, the price of hydrogen is an important component of that, but we can do quite a bit of sensitivity analysis using different price points for, of course, jet fuel and hydrogen. So this is pretty close to the end. Of course, this is jet zero, and net zero is very important component of government strategy. And I actually a great supporter of UK government is doing, and supporting doing things which are very different from lots of other countries, and being on the forefront and setting the very ambitious goals in terms of actually the emissions. That pulls all of us, researchers, all the industry together to actually try to achieve the goals which are set up by the government, by the humanity. And we are recognized, for example, by inclusion. We are the only startup which was included in the Jet Zero Council, which is working towards development of the pathway to towards zero emission flights by 2030. And we were covered, this is our aircraft at the presentation of the Jet Zero strategy. So we love to work and do what we are doing. We love to live a dream. And this is, compared to some of my previous work, I was working in the consulting industry for about a dozen years. I think that this is actually, a better thing to do. And, waking up in the morning is, has a lot of meaning to me and to a lot of to all of my team. So thank you very much. I hope I conveyed the message that, what we are doing is important and that, doing step by step and incremental demonstrators of technology, we will be able to achieve our goals. Thank you.
Sergey, that's a fantastic story. Thank you very much for telling us about it. You've left us some time for questions. I'm sure there will be plenty. I think we need to sort of stand so that we can't see, we're not appearing on the Zoom screen, but we need to stay within range of microphones.
Okay.
Great. So the deal is, if you would like to ask a question, please wait for a microphone. And if you're online, please put your question in the Q&A on the online, and I'm getting them here. Right. So let me start online. What did you study as an undergraduate?
I studied physics and math and in Moscow, and then I went to graduate school to the United States. I studied experimental low temperature physics at Cornell University.
And then there's someone, we have some questions about the crash of a Piper hydrogen plane.
Yeah.
With a suggestion that it was due to a fan power back disabled the engine at takeoff. Is that right?
So our original aircraft was actually, it landed off field of the airport, and there was of course the investigation of why that happened, and actually it had nothing to do with hydrogen and the hydrogen powertrain. It was mostly due to the electronics, and of course we took all the necessary measures to make sure that it doesn't repeat again. And now actually it's as I said, it was the last 2 years were quite a journey for ZeroAvia, and so we went from sort of the fast realization of our thoughts, and do basically like I wouldn't say the garage type of work, but we went through the rigorous CIA approved processes in terms of how you design, what type of processes you use in designing the powertrain, and then implement it. And then CIA, for example, was today witnessing our tests at the airport. So we basically had to implement all these necessary steps to make sure that when we actually start the journey to certify our powertrain, we will not have the situations like what happened about 2 years ago.
I probably shouldn't have started with those questions. We have some questions in the room.
David Peregrine.
Yes.
You opened your lecture by saying that a battery plane could have, a large one would take 80% of the weight for the battery. How much is your current propulsion system and storage system weighing as a percentage? And what do you expect the larger plane to end up with?
So good question. So I think that that actually depends quite a bit on the mission. Okay, so for the long distance flight, there is quite, of course, a bit of fuel which is used to fly, for example, across the Pacific Ocean, right? So I think that the weight of fuel is can be tens of percent. So let's say something like 20 to 30%. So and this is quite significant, but it's not what you would expect from the battery electric aircraft. So the maximum. So for example, for the 19-seat aircraft, the maximum mission you can achieve without the loss of the passenger intake or cargo capacity is something on the order of I would say between 60 and 80 kilometers, compared to a couple of thousand kilometers which you can fly on traditional fuel.
There's a little way to go. Someone the microphone. Sorry, the lights in my eye. Right at the back. Yes.
Thank you. Trevor Cave, aerospace man, but I have actually been involved in a land speed record electric car. And to the best of my knowledge, no land speed record car has tried to use fuel cells because of lack of power density. But not trying to nitpick that, can you give me an idea of the overall conversion efficiency, electricity to hydrogen and hydrogen back to electricity of your system? Otherwise, you're going to need tens of square miles of solar array, aren't you?
So the back-to-back conversion efficiency is of course much worse than for the batteries. So for the batteries, it is something like 90%, right? So here our hydrogen fuel cell has about 50% efficiency, okay? And on top of that, there is a bit of loss of power in power electronics and electrical motor. So you can say that the overall efficiency is on the order of 40%, okay? 40, maybe even plus %.
Is that just from the hydrogen?
So from hydrogen to the propeller.
Electricity through the electrolyzer to the hydrogen as well.
So something it will be something on the order of 25%, 25, 30. No, electricity to the propeller, it is about 90+%. No, it will be about quarter. So you lose on the on the stage of the electrolysis, and then out of that 50% gets to the propulsion. You need to have either a lot of solar farms, or you need to have a lot of wind farms, offshore wind farms, or you can use nuclear power generation to produce a lot of hydrogen. But it is there is no alternative, right?
That was a helpfully direct answer. Thank you. Yes, I agree. That's my estimation as well. Right.
Thanks for a great talk, Sergey. What's the nature of the hydrogen storage on board? What kind of technology do you have in the storage tank? Because hydrogen can be a tricky thing.
Yeah, so currently for the 19-seat aircraft, we are using composite tanks, which are using gaseous hydrogen compressed to 350 atmospheres or 350 bars. And this is very similar to what Toyota Mirai is using inside of their cars. Okay, and actually composite tanks are very safe, and they go through the very interesting testing. They shoot I think 45 caliber guns to actually see if it's if it leads to the explosion, and it doesn't. Okay, so but those tanks are tested to about 3 times of the working pressure, you know, between 2 and 3 times of working pressure, and they're very safe. And during our off the airport landing, by the way, the storage tanks are actually probably the most robust you know, place on the aircraft. Now, when we go to the larger aircraft, we would need to use liquid hydrogen, and that is you know, sort of the cryostat or the dewar type of arrangement to store hydrogen.
That will not happen for a while. The liquid hydrogen, that's a pretty complicated infrastructure.
So we are actually testing, going to test this this infrastructure at the beginning of next year. We will have our own liquefier, and we will have our cryogenic tanks to actually store and then use liquid hydrogen.
Right.
Thank you very much. Somebody asked my first question. My second question is, because the aircraft is propeller driven, does that mean you will be flying at lower altitude, and we'll be back to the rather less comfortable flights that we used to have with propeller aircraft?
So that's a good question. So on the propeller aircraft, we typically don't travel long distances, right? So, and especially on the 19-seat aircraft. So the missions will be something on the order of, I would say, less than an hour, typically. And it is regional and sub-regional operations. Now, the aircraft which you see here, it is not going to be a pressurized cabin. Okay, so by design, the highest altitude it is typically operated is something on the order of 10,000 feet. Now, if you go to the pressurized cabin, then of course sky is the limit, and you can fly it at higher altitudes. Now, the problem with that is that the hydrogen fuel cell uses hydrogen and oxygen from the air, and when you go to the higher altitude, there will be less and less air, right? So you would need to compress that air which comes into the hydrogen fuel cell more and more. It's not going to be a problem in our applications, but you still this is one of the requirements to design our powertrain in such a way that it can operate up to higher altitudes.
One of the online questions is what sort of speeds can be achieved in a propeller-driven aircraft? I guess it's the same as today's.
Yeah. Absolutely.
Yes.
And this is one of the reasons we are actually doing the way we are doing. We are our first introductions into commercial aviation will be by retrofitting the existing aircraft, because you don't need to certify the aircraft itself. You need to certify only the power.
And the aircraft is designed to travel at a certain altitude and a certain speed,
yes.
and you'd adjust to do that.
Yeah. So we one-to-one match our power parameters.
Right. And I've got lots of online questions. Can I grab one more of these and then go to the audience here? If I can paraphrase, why is everybody else spending so much time on electric battery driven aircraft?
Actually,
to put it bluntly. Yes.
actually, it's not that many people who are putting a lot of energy. There are a couple of companies which are working on it, but they realize that it is it is going to solve the short distance missions, and actually with some of them we are discussing the opportunity of working together and actually replace the batteries for hydrogen fuel cell technology.
I can't help picking up on something you mentioned in your presentation, or one of the disadvantages of batteries. It's always fun saying how everybody else's technology doesn't work, but they don't actually recharge that many times before they lose capacity. So if you knacker a battery once a day, 365 days a year, then it needs changing. Was that what you're hinting at?
It's one of the major drawbacks of this. You need.
I just wanted to check. There's a question somewhere in the middle. Yes.
Thank you. So I think, if I'm right, with the Toyota hydrogen car, they have the fuel cell powering a battery, which then powers the motors. So you've got instantaneous power. Do you have the same kind of buffer battery arrangement, or are you able to modulate your hydrogen power sufficiently?
Yeah. So for hydrogen aircraft, you don't actually need to. I mean, Toyota cars, they go, they accelerate, decelerate all the time. With the aircraft, you reach, you put it in maximum, pretty much power. You go to your altitude and then pretty much cruising at the same speed. So we are able to achieve the operational parameters of the hydrogen fuel cell system in such a way that it can satisfy the requirements of the climb, and then the modulation, during the cruise is not an issue. So we are not using the battery as a buffer. And actually, that simplifies the design quite a bit, and it will simplify the certification of the powertrain going forward.
Just a couple of things. How do you regulate the output of the powertrain?
So the way we regulate the output is that we are demanding the amount of power and the torque from our controller. Okay, and that will. So we are demanding certain power, and that means voltage and current from the hydrogen fuel cell. And it is just it's delivering it.
Is it resistively controlled?
It is.
So you've got ohmic heating somewhere on board. More power.
It is. So there is a lot of heating. There is a lot of heat generated during the operations, but it's not resistive heating.
Slightly off your topic, but this goes back a few years. I think the late 60s, early 70s, Lockheed took a standard aircraft, chopped the middle out, extended the fuselage, stuck in a hydrogen tank. It worked beautifully. Now, it solves all the carbon problems. It doesn't solve the NOx problems, but is that not going to be overall, by the time you take into all your compression, your cryogenics, your batteries, you're going to actually turn out to be a more efficient way of doing it than having a whole pile of kit hooked together, which weighs a devil of a lot? You actually save weight in the Lockheed machine because you've got hydrogen instead of kerosene.
I mean, at the end of the day, there is different technological maturity of different options, right? So the Lockheed, or what the Soviet Union with I think that Tupolev 154 or 134, whatever, they did exactly that. Okay, so they burned, they use hydrogen combustion on the aircraft. They demonstrated that, but at the end of the day, you will end up with a lot of emissions, right? So with a lot of NOx and all the induced emissions, which are still going to be there. It is much better And the benefit is that you can eliminate between. So there was a research which showed that if you're using combustion, you can eliminate up to, let's say, 60% of all the of all the environmental impact, but 40% will still stay there. While with hydrogen fuel cell technology, you can eliminate north of 90% of emissions, which is quite a significant difference if you think about that. And of course, it will be heavier, but
so we now have 17 questions online. So I'm going to sort of amalgamate some of them, but let me have a go. There are questions around what you have to do to get flight certification. Is it harder to fly because the weight balance has gone wrong? Do you have a flight plan to get these things in production or in real use?
So, of course, we have to make sure that the aircraft has a proper weight balance. You cannot.
I presume that you have to get that right.
Yes, you have to get it right. And this is some of the drawings. We have, I think, 9 different configurations how we can actually put our powertrain and the storage inside of the Cessna Caravan. And this needs to be done properly, and this needs to be done in a similar way as the original aircraft is done.
And to whiz quickly through some of these questions, what about the hydrogen storage and risk of a Hindenburg event?
Yeah, in Hindenburg, actually, it's.
So I don't want to divert you for too long on that.
It's a very popular question, but it turns out that in Hindenburg, actually, I think that aluminum shell was burning and not hydrogen itself. Okay, so in our case, for example, if you place hydrogen on the wings under, like here, under the wing. Actually, it's very favorable configuration because the compressed hydrogen is actually placed, you can see that the 19-seat aircraft in the middle. So it is hydrogen is outside. If there is any leak in high pressure system, hydrogen will go, outside of the aircraft and up in the air.
So I've got a number of sort of questions I'll put together about power to weight ratio or energy to weight ratio. Which may affect ultimate range, but also questions as to how that splits between the motor, the fuel cell, and the stored hydrogen.
Yeah. So just some figures of merit. You remember I mentioned that we are working on the achieving the best power density for the hydrogen. For the electrical motors and the hydrogen fuel cells. So the electrical motors have we'll have something like 15 kilowatt per kilogram. Okay, so the power electronics has something like 25 kilowatt per kilogram, while hydrogen fuel cell systems will have on the order of 2 to 3 kilowatt per kilogram. So from this, you can infer that, of course, the most problematic part is the hydrogen fuel cell.
And switching to the high temperature system gives you twice the energy density. Yeah. And how does that
power density?
Sorry, power density. And what about the hydrogen storage? If you got the weight down on all those components, how much difference does that make?
Typically the weight, especially for liquid hydrogen, is not a problem. The volume is a problem.
It's the space it takes.
Yeah. So because hydrogen is the most energy dense energy media
per kilogram, but not per liter.
Yeah, exactly. That's why the volume is a problem. That's why we have some of the renders. For example, the flying wing kind of configuration, which will have a lot of space, and it doesn't. It will not have a lot of weight.
Okay, let's head back in. There's a question at the back.
Hi, Shannon Bonker from Cambridge Chemistry. It's a really interesting concept. So are you or is ZeroAvia essentially betting that the levelized cost of electricity will drop enough that you'll be cheaper than other sustainable aviation fuels? Would that be a fair synopsis?
Yeah. So in general, sustainable aviation, there are two ways to get sustainable aviation fuel. One is, of course, from the feedstock, which is limited, and another is the so-called e-fuels, which use hydrogen as a feedstock. So the price of e-fuels. So while the first is limited, the price of e-fuels is going to be considerably higher than even hydrogen.
So I had always presumed that the economic model would be that if you have renewables, there'll be times of excess production of electricity, at which point the spot price of electricity is very low, and that's when you make your hydrogen, which would require a more integrated access to the electricity system. So making hydrogen at night time when the wind blows and people have gone to bed.
So this would be, of course, the most beneficial for the cost of hydrogen production when you have zero or negative prices. But unfortunately, if you have situations like that, then the times, like in Orkney Islands, for example, which has a lot of wind capacity, but very weak link between the island and Scotland, then the times when there is negative prices, negative electricity prices, is something like 30% of all the time. But you cannot invest your money into building electrolyzer, which will be used 30% of the time.
Okay.
Right. So then it will be, you would like it to be something like, north of 60% or better 80%. So that this effective capex will.
But essentially the proposition is that zero negative price electricity, the easiest thing to turn it into is hydrogen. There's not much else you can do with it, or pump it uphill or something. But
yeah, you can do that if you have hills. Yeah.
Can I just follow up on that, because you led into it perfectly when you talked about e-fuels, because wouldn't one argument be that rather than trying to store liquid hydrogen, which is a noble aim but going to be quite energy intensive in itself, of course the obvious argument would be to utilize that hydrogen, turn it into e-fuel, or however we want to market it, considering that would essentially be a liquid hydrogen carrier, if you wanted to phrase it in that way. Is there a particular reason that ZeroAvia is going very much in the opposite direction? Is there something you see that I don't?
So with the e-fuels, again, the price of e-fuels will be significantly higher. Yeah, but then you will need to add. So you produce hydrogen, and then you need to spend more money to convert it into the carbohydrates, right? So that's number one. And number two, you still have induced environmental environmental impact from it's still the combustion, right? So the NOx, the soot, contrails, etc., they will still be produced. So you will eliminate the direct CO2 emissions, but all the induced emissions will still be there, right?
Okay, we have a fantastic number of questions. At some point, we might have to switch to the bar to carry on. But
hello.
Yeah.
That answer follows in quite nicely to my question, because I was going to ask what level of certainty you have when it comes to the non-CO2 effects of hydrogen cells, but also competitor solutions such as hydrogen combustion and SAF. For example, I think Airbus are doing a lot of work trying to prove that the issue of contrails from hydrogen combustion isn't so bad.
I would say that there is quite a bit of research going on right now. And of course, I was in May this year, I was at MSN1, this A380, which Airbus in Toulouse is converting into this flying platform where they're going to put additional turbine where they're going to combust hydrogen. And this will put much more light into, and get much more certainty in terms of what is the induced environmental impact from hydrogen combustion. Yeah, but I would say that the data which we are operating with is it's not recent. It may be a few years old. And every single year, I would expect that we will get better and better data and better understanding. I know that, for example, German lab or research institute is doing quite significant research on that front as well. So we will have, of course, much more certainty going forward. But this is what external reputable sources are giving us at this point.
Is that DLR
yeah.
there?
Yeah.
And do you have much data around the impact specifically of fuel cells, for example, on the graphic you displayed earlier? I think it indicated still some moderate impacts around non-CO2 effects, so still some residual effects.
So there can be some residual impacts which we also can eliminate, but that is a different topic. But mostly it will be coming from the fact that the water or the water vapor which comes out of the aircraft, it can still produce certain impact, right? On it's not a big source of environmental impact at the low altitude, but if you go higher, then of course it will be higher impact. But we have a solution for that as well. So, for example, you can freeze the water. It can drop down and it will melt when it reaches the ground.
Yeah, I really hope that melts first before it reaches the ground. Thanks.
I think we can take another question. Yep. Right at the back, is there? Or?
Just over here. Hi, if I could just ask about ZeroAvia's sort of value proposition, because when it comes to creating sustainable solutions, we also need sustainable businesses for the application of our research. What do you see as the roadmap to monetization of ZeroAvia? And certainly in the 19-seat sector, we see real low margins and difficulty in converting businesses to profitability with the likes of Loganair and Flybe. Do you see them with an appetite for the investment in this new technology? And indeed, how does that convert to your monetization of this technology?
So in terms of monetization of the technology, of course, we are cash negative business at this point, right? But we foresee that after we enter actually into the into commercial operations, and we anticipate that it will be in 2025. After let's say 3 years after that, we will actually start to break even. Okay, and that is coming from two facts. First of all, powertrain needs to be either of the aircraft on turboprops. It needs to be retrofitted significantly more often than the lifetime of the aircraft itself. Okay, and roughly we can achieve something like 2x of the lifetime of our powertrain compared to the traditional powertrain. That's number one. And number two, we can bring significant savings, as you can see from again, of course, depending on the relative price of jet fuel and hydrogen. We can bring significant savings to the operators. Okay. And in terms of the turboprops and then larger aircraft, which we think that we can put actually into operation by the end of this decade, we already have more than 1,000 orders or pre-orders for the engines, and the sale of either engines by themselves or some sort of power by our model combined with the supply of hydrogen will actually bring commercial viability to our project.
Okay, so we've entered on a sort of practical question issue. I mean, this is the Cambridge Society for the Application of Research, so the application bit is an important part of the mix. I'm going to stop there because we can all adjourn to the bar. There might be some wine left over from the drinks that were available before the lecture, and I think those bottles of wine will have migrated to the bar, so don't all go rushing all at once. But Sergey, thank you. That was a wonderful lecture. You can see what interest it's generated. I hope most of those in the audience managed to get their questions in. I am conscious that I did quite a bit of amalgamation of quite a huge number of questions online. So you've stimulated a wonderful level of interest. Thank you very much. I noticed that your final slide seemed to show a faster sort of tenor of prime ministers than your ranges of aircraft. So I hope you managed to overtake our world record in that direction. But thank you very much. Finally, let me say that in 2 weeks' time, we have Tom Peacock, who's going to talk about the Rolls-Royce small modular nuclear reactors. But again, Sergey, thank you very much.
Thank you.